Welcome to a lesson with Dr. Powell. Let's look at an argument due to Cantor that a set can never be in bijective correspondence with its power set. Now, let's assume that it can. All right, let's assume that we do have a bijection from here to here, and we're going to find a contradiction. But first, before we go through that, let's look at a particular case. Let's look at the case for the natural numbers and to its power set. Because if we do this, we can have a visual called Cantor's diagonal argument in this case, and then we can generalize it. Okay, so let's suppose that we have a bijection. In fact, we're just going to use the idea of surjection and show that we can't have a surjection. So therefore, we won't have a bijection. So let's assume that F is a surjection. Okay, meaning that let's just take the domain and list them out, because that's what N allows us to do. We can form a list. All right, so these are the elements of the domain, and kind of think of a function table. This is like input and output. Output would be a subset of N. Now, subsets, we can use binary notation if we want to. We think of all the different elements of the natural numbers, 1, 2, 3, 4, 5, 6, and so forth. We could think in position 1, is 1 an element of that subset or not? Maybe it's not. Is 2? Maybe 2 is. Maybe 3 is. Maybe 4 isn't. Maybe 5 isn't. Maybe 6 is. We get a sequence of zeros and ones, which represent a subset. So basically, subsets are sequences. Sequence can be encoded as sequences of zeros and ones, indexed by the natural numbers. So this is just an example of a function f. So let's just suppose we had any surjection function f, surjective function f. So for instance, we could just kind of list a few things out. Maybe we have 0, 0, 0, 0, 1, 0, 0, 0, 0, maybe 1, 1, 1, 1, 1, 1, 0, 1, 0. Okay, we have something going on here. Now, you see this diagonal right here? It is a code itself for a subset. What if we were to take its complement? Now, its complement would read something like 1, 0, 1, 0. I'm just looking down this list and switching the zeros and ones. Okay, so we get the complement of the set. Now, let's think about this as we go here. And so it'll go like this, all right? The idea is that we want to create a subset of, or we want to find a subset of S, or of N in this case, such that it's not in the image of this function. So we want to create something that's not going to be in this listing. Let's think about this. Well, this differs from the first thing in the listing by the first guy, the second thing in the listing by the second guy, the third thing in the listing by that guy. In fact, anything in the list, it'll differ by it in at least one place. Hence, it's different than anything else in the list. So therefore, it's not in the image of this surjection, no matter what surjection it was. Because no matter what surjection it was, we could make this list and go the diagonal route and take a complement and get something that's not in any of these rows. So therefore, we've found that, and F has something it doesn't ever hit, so F cannot be a surjection. So that contradicts the idea that F would be a surjection. Okay, so this is in the case for N. Now let's try to generalize this a little bit, so just for an arbitrary S to our power set. Okay, so kind of thinking along these lines, let's suppose that we have a surjection, right? And we want to find a set. So if we choose the following set right here, and it's going to be based upon the definition of F, let's select all x in S such that x is not in its image. in its image set. So its image is going to be a subset of S, right? So how does that mirror what we just did with the diagonal? Well, okay, so um, let's see, X itself, all right? So the image of X, so let's suppose X is 1. The image of X is all of this, right? It's a subset. And it has a particular notation like this, right? So let's suppose that, well, first of all, 1 is not in its subset right here, is it? Okay, but so that means that we would include, so 1 is not, so that means we would include 1. Notice we're including 1. Now, what about 2? Notice that we include 2 right here, but we wouldn't include 2 now because actually that position means that 2 is in its image. So this tells us not to include it. So we don't include it. This one right here, we're including 3, and let's see why. Because at 3, so imagine 3 is like X, and notice that it's not in its image, so therefore we switch it to a 1. So it's like we're using the same technique to build this generally. Okay, so this is going to be the construct. Suppose this is our set that's going to live in the power set here that's not going to have an image. Can we show that it doesn't have an image? Let's try it. Let's suppose that it did have an image. Let's suppose that y perhaps maps to it. So that would be like f of y is equal to b. Let's think about what that means. Then there's a question. So is y in b or is it not in b? Well, we have two choices. Okay, if y is in b, which is in f of y, that means that y is not, according to this definition, let's see, y can only be in this if it's not in its image, so therefore it can't be in it. So y is not in, so y can't be in b. But wait a minute, this was b. So we're saying if y is in b, then it's not in b? If y is not in b, then that actually means that y is in this set, which is in b. This right here is our contradiction. This means that since this is ludicrous and false, we can't have something in a set and not in a set at this exact same time, which means that f of y couldn't have been b, or f of y couldn't have been this set at all. So that means this set is never hit. So that means that this can never be a surjection, therefore never a bijection. So a set and its power set can never have the same cardinality, and they can never be in bijective correspondence with each other. Thanks for watching.